Greetings, Science Maximites. My name is Phil, and today on Science Max Experiments at Large, we are using mouse traps, but I cannot find my mouse traps, so it's gonna be a little hard to do the experiment unless I have... Oh, hey, here they are. Oh yeah, I stored them preset. Why would I do that? Okay, well that's fine. Anyway, today we, careful, are going to be using mouse traps. Like I said, we are going to be using mouse traps. Mouse traps as a form of propulsion. That's the force that makes things go, and we are going to be making a boat go. And what is the thing that's going to make this boat go? A mouse. Oh, it's not set. Sorry, I'm really jumpy. Anyway, we're gonna be using a mouse trap. And don't worry, no mice are gonna be harmed in the making of this or any Science Max episode, but mouse traps are really great because they can store energy in the spring. If you see, there's a spring that makes this bar want to snap back, but we can put energy into the spring and store it and then use that energy as it unwinds the spring to propel our boat. But it's a little more complicated than just this, so come on, I'll show you. What we're gonna do is build this. This is the mousetrap boat, and it works like this. I've got the mousetrap, and it's attached to a long arm. That arm has a string on it, and it goes around the paddle wheel, and as the mousetrap unwinds, the paddle wheel spins like that, which pushes the boat forward. Now, it looks kind of complicated, but it's actually quite simple to make, and here's what you need. My mousetrap boat is made with styrofoam, craft sticks, and elastics. You'll also want a pencil, plastic drink caps, a shish kebab skewer, small zip ties, string, and of course your mousetrap. Now, mousetraps can hurt your fingers, so get an adult to help you when you use them. Start with 2 pieces of styrofoam. I like to cut mine into this shape, but the only really important thing is that they're the same size. Your paddle wheel is made from a circle of styrofoam with it penciled through the middle, and it will go across like this. To make the paddle wheel, I use cut pieces of craft stick, or they can be plastic, and make some cuts and then put them in like this, and that is what will make your paddles on the paddle wheel, because that's the wheel and that's the paddle wheel. That's why they call it that. Stick drink caps to the ends of the pencil after sticking it through the styrofoam. I like to use a few craft sticks and elastics to help give the styrofoam strength. Next is the mousetrap, which you want to glue down to a frame of 4 craft sticks. Attach the frame to the boat with elastics, then attach the shish kebab skewer or a pencil to the mousetrap with zip ties. I like to put some craft sticks on the end to make it easier to tie the string to it. Wrap the other end around the paddle wheel pencil, and remember you need enough string so that your stick can lie flat. Okay. Let's try it out. Wind up the paddle wheel. This'll be a little hard as the spring will pull back, but that's where you're storing the energy. And when it's wound up, put it in the water and let it go. The paddle wheel turns because the mousetrap is transferring energy that we put in earlier, and it goes all the way. We stored the energy in the tension of the spring. Now that tension is pulling the mousetrap, the stick, and the string, which turns the paddle wheel and makes the boat go. Mousetrap-powered boat! If you want more detailed instructions or other designs, look up Mousetrap Boat. And there you have it, the mousetrap-powered paddle wheel boat. And this is what we're going to max out today. Come on. All right, time to pick an expert and go off to max it out. Careful. Okay, let's see here. And, who to pick? Michaela from the Ontario Science Center. She'd be perfect. All right. Come on. I ended up in the water again. Oh well, at least maybe Michaela made it. Oh, Michaela!
Whoa, Phil!
Are you okay?
Are we still fixing the portal?
Yeah, I needed to tweak it just a little bit. It's a little off again. Anyway, great to see you, Michaela from the Ontario Science Center. You're gonna help me max out the mousetrap boat.
Awesome.
Yeah.
Wait, where's the boat?
I don't have it. I thought it was gonna come through the portal. It could be anywhere, really. I mean, What? Oh, here it is. Okay, good. So, here is the mousetrap boat. check it out. So, got a mousetrap here, right? And you wind up the paddle wheel, and it goes. Yeah, right on.
Awesome.
So, what do you think we should do in order to max this out?
Well, first idea, I'm just thinking more mousetraps.
More mousetraps. So we just make a boat and it has like 10 mousetraps on it.
At least.
Okay, great. Actually, I had mousetraps coming through the portal as well.
Okay.
Oh. Okay. Okay, we're all right. Okay, so now we've got the mousetraps. We can start building. Let's collect them carefully, though. I don't know if they're...
Initial thrust or constant thrust. What's the difference? It's all about power. Uh-oh. Paper airplane initial thrust. It gets all of its thrust from my throw. Initial thrust. If you want constant thrust, you have to take the thrust with you, like this. There's a lot of cats in here. Initial thrust. Initial thrust. Initial thrust. All the energy is put into the beginning of the... All the energy is put into the beginning. If you want constant thrust, then the thing has to produce power while it's moving. Wind up car, constant thrust. Actual car? Yeah, that's constant thrust because you have an engine. Of course, not this car. This is a toy car. But you know what I mean. Check out this fishing rod, and on it I have a lure with a hook. Now watch this. I cast it out, initial thrust, but then I use the reel and start winding it back in. Constant thrust, huh? Two thrusts in one. And now you know the difference between initial thrust and constant thrust. Hey, I caught a fish. Hey. Oh, easy, kitty. Nice kitties. Easy, Ramona!
Michaela and I are maxing out a mousetrap boat. We built a larger version with 10 mousetraps all in a line. So it looks pretty good. I think we're ready, right?
Yeah, I think so.
Got a whole bunch of mousetraps. Should we wind it up and see
All right.
what happens?
Let's do it.
I think this is gonna go pretty well. What do you think of that stick? Is that gonna bend too much? Is that gonna snap or?
Looks pretty flexible.
I mean,
I think we're okay.
I think we just keep going until it breaks. Ooh. Now it's starting to look very fast. Yeah, like it looks like a speedboat. Okay, ready? Go. Well, positive. It is working.
It's not gonna win any speedboat races.
It is not gonna win any races at all. But it's totally working. The mousetraps, they're pulling on the string. The string is making the paddle wheel turn. Just not much. I would have thought this many mousetraps would be a little bit more effective.
Yeah, it looks like we're going for distance over power things. See,
Oh,
we're
right,
using
because-
a lever here. That's a lot of distance for this to travel. But if
Small
we
amount of force over a much longer distance, that's how a lever works.
Exactly.
So we slide the rope down further on the stick, then we would get more force, and it just wouldn't go as long. Okay, so why don't we try that? Wrapping, like that.
Nice.
All right, once again.
Trial 2.
Okay,
Okay.
ready?
Ready, set.
Go! Ah!
Hey, that looked better than last. Oh, now it's picking up.
Yeah, that's really working. Whoa, careful. Oh, look out! Look out! So, good. It's good.
Okay.
It's not great. Not yet.
Yeah,
Right? How do we make it better? What do you think?
Well, I was thinking, what if we try to reduce the friction? Remember that other boat we tried?
Here it is.
Oh, yeah.
The little one, you mean?
Yeah, the little one. See, look at this one. It has a pontoon style. Do you see how we have it floating on these two surfaces?
Yeah.
So very little is actually touching the water. Whereas
Oh.
this one, we have a giant hull that's going to drag the water and slow our boat down.
So it's sort of like the difference between like pushing a whole bunch of water like that and pushing the water like that.
Yeah, we want very little resistance for our boat.
So little resistance with a couple things that just stick down like that. A lot of resistance when we have big, flat, big, like that. So we completely rebuilt this boat. Shall we do it?
Yeah, let's do it.
Our tools floated away again.
Oh.
Race ya!
Mini
our maxed out mousetrap boat isn't the only way to give a boat propulsion. Let's look at another way using a balloon. Let's make a balloon-powered boat. All you need for that is something to be your boat and a balloon. Then you attach them together. Actually, the best way to do it is use a straw and attach the balloon to the straw using an elastic band. And then you attach it to your boat using more elastic bands, just like this. I've put a nice tape top on the boat to make it look awesome. And I also put a little bit of a riser here using just anything plastic to keep the straw nice and straight, because the question is, will our balloon-powered boat work better if it's pushing in the air or if it's pushing in the water? Well, let's do a science experiment and find out. First version, in the air. Oh, almost all the way. Now let's try it with the straw like this so it pushes into the water. Whoa, works so much better. Why? Because water is denser than air. The air coming out of the straw has to push against something to make the boat move. Water has more mass than air, so pushing against water has a better result. Now, let's max it out. This is an air compressor. Well, actually, that is the air compressor. You see, the engine here pushes air into this tank, which works sort of like the balloon. And then it goes out this long hose, which sort of works like a straw. So let's make a maxed out air-powered boat. Ready? Just like the small boat, pushing against the air doesn't produce much thrust. Not so great. But now let's put it in the water. Pushing against the water gives me much more thrust because water is more dense than air. Whoa. Maxed out air-powered boat! Maxed out air-powered boat! Yeah! Whoa! That's not me. Michaela and I are maxing out the mousetrap boat. 10 mousetraps didn't seem to make our boat go very fast, but moving the string down our lever arm helped, and now we want to redesign the hull so it has less friction with the water. Check it out! This is the ultimate mousetrap boat. We got 10 mousetraps here. We got our long arm. We have it attached at the right point of the lever, we think, and then we've got two paddle wheels at the back and pontoons.
Yes.
Yeah, so what do you think, Michaela?
This thing is set.
It's gonna be awesome?
Yep.
Okay, ready?
Ready? Let's test it.
Whoa, it's working.
Hey,
It's working.
It's picking up speed.
Yes.
Wow.
Whoa, mousetrap boat. I mean, it's good. It's good. It's not Science Max good.
Yeah. We were hoping it would go faster.
Faster or... No, pretty much just faster. Yeah, okay. Obviously, we need to store more energy. That will make the paddle wheels go faster, right?
Yeah, so we just have to think about it, right? Like, what's stronger than a mousetrap?
Well, 10 mousetraps. That's why we have 10 mousetraps, Michaela.
Okay, what's stronger than 10 mousetraps?
11 mousetraps? Like, if we just keep going and
Okay,
it's just
enough
gonna
with
get
the
super
mousetraps.
wide, we have 1,000 mousetrap wide. What?
Enough with the mousetraps. Have you ever seen, like, a rat trap?
No?
They're huge.
Well, hold on. I can just get one from the portal. One rat trap coming up. Oh, okay, Kimber. All right, well, that's fine. And whoa!
Wow!
Yeah,
look at
that is a lot bigger. Okay,
Huge
so snap
difference.
yours.
All right,
Is it?
ready? Mousetrap.
Okay.
Okay.
That's terrifying. So that's a lot more power.
Yeah, a lot of force.
So tell you what, we have a little mousetrap boat. Why don't we build a little single rat trap powered boat and we'll race them and we'll just see the difference in power from one rat trap to one mousetrap.
I like that. We'll do a prototype before we make a big one.
Yeah, okay, come on, let's go. So we built a rat trap boat to race the mousetrap boat. And then Michaela and I got a little competitive.
Check out the rat trap boat.
No, check out the mousetrap boat. Mousetrap boat is better because...
Yeah, rat trap boat is better. It's got bigger springs, more potential energy stored in here.
And mousetrap boat has less potential energy and less springs, but he's got more heart, and he really wants to win.
Hey, yeah, I'll tell you what, Phil. Loser jumps in the pool.
What? Oh, okay, sure, let's do it. Okay, ready? Go! So, as you may have guessed, the rat trap boat has a lot more potential energy that can be stored in the spring. Okay, so rat trap boat is clearly better than the mousetrap boat. We make the boat the same way,
Yeah.
but we use rat traps instead of mousetraps. What do you say?
Love it.
Okay, let's do it.
Let's do it.
Yeah.
Wait a second, Phil.
What?
Fair's fair. You gotta jump in the pool.
Okay, fine. Here you go. Hold this. Inertia. What is it? Well, it's directly related to Newton's first law of motion. An object in motion tends to stay in motion, an object at rest tends to stay at rest. Let's do an experiment. Here is an object. Right now, it's at rest. You might think that means it has no inertia, but that's not true. Inertia just means an object's tendency to keep doing what it is doing. Right now, it's doing nothing. But if I wanted to overcome its inertia, I would have to put energy in. And now that I have, it is moving on its own. It has inertia. If I wanted to stop it, I would have to overcome its inertia, its tendency to keep moving. There. I went exactly that far. Now, let's max it out. I'm adding these weights to the cart. Now it has a lot more mass, which means it has a lot more inertia and its tendency to do nothing. But this time it has a lot more inertia. If I wanted to get it going the same speed as before, I'd have to put in a lot more effort. There, now it's going the same speed as before, but now it has way more inertia, so stopping it will be harder. So there you go, inertia. A thing's tendency to stay moving or stay still, and the more mass, the more inertia. Dear Phil, I can't believe you did a whole episode on boat propulsion and you didn't use the greatest thing out there for making a boat move, a propeller. Sincerely, a fan. Well, let's talk about propellers. Oh, good thing this is fan mail. Get it? Because it's a fan? Yeah, anyway. A fan pushes air just like a boat propeller pushes water. They're both fluids and they behave in the same way. Now, if you look closely at a fan, it's curved on the blades. The air or water is caught under at this side and then it's pushed out on the curve to make it go that way. And the faster it spins, the better it works. Now, this is a propeller-powered boat. And what you do is wind up the propeller. I have an elastic band here to store the amount of energy I put in. And then you put it in the water, the propeller spins, and the boat goes forwards. It's being propelled by the propeller. That's why you call it that. Awesome, right? Well, now we'll max it out. This is a drill. It spins. And this is a propeller, and when you put it in the water and spin it, it provides thrust. So let's try it out. Whoa! Remember not to try this at home. I am a trained professional. This is a very small propeller. Let's compare. This is a super maxed out propeller. Whoa, okay, let's try it out. Whoa! The larger a propeller is, the more energy you need to turn it, and the more propulsion you get out. Michaela and I are maxing out the mousetrap boat. Well, actually, we can't call it a mousetrap boat anymore because now we're using rat traps. The design is the same as our 10 mousetrap boat.
Rat trap boat! Rat trap boat! It's the super most rat trap boat ever!
We wind it up and try it out.
Okay, ready? Go!
It worked great. The reason is because this boat was storing a lot more energy in the spring tension. More energy means more propulsion. So much, we couldn't even catch it.
Yeah! Rat trap boat! Science Max, experiments at large, rat trap boat, high five. Let's do it again.
This episode is all about chemical reactions.
Nom nom nom, nom nom nom, nom nom nom, delicious.
Reactions to make things fly, to make things glow, to make things pop, and to make things fly.
That worked.
Wait, did I mention the flying? I'm sure I did, but I'm mentioning it again because it's awesome. All on this episode of Science Max Experiments at Large. Okay, Science Maximites, prepare to hurtle through the cosmos. I am Captain Phil, and today we're going to be building rockets on Science Max. Now, we've built rockets before, like this one, powered by air pressure. And this one, stomp rockets, which were also technically powered by air pressure. Air pressure rocket! But today, Science Maximites, we are going to be building rockets powered by chemistry! Chemical-powered rockets! Away! Okay, I promise it'll be more exciting than that. Because today, Science Maximites, we are going to be looking at chemistry. Chemistry is when two molecules combine to make another molecule. Like magic, ooh. So let's take a look at what will be powering our chemical rocket. This, it's an antacid tablet. When you put an antacid tablet in water, it makes little bubbles of carbon dioxide gas. This happens because of a reaction between two kinds of molecules called acids and bases. Like vinegar and baking soda, but all contained in a small package that won't start working until you put it in water. If we contain the reaction, the carbon dioxide gas builds up and creates pressure. High five for science. All right, so let's look at our chemical-powered rocket. What you need is one of these. This is a film canister. And ask your parents what that actually means because they're not used for holding film anymore. You can get these at craft stores, though, to hold paint or little things. But really, all you need is a plastic container with a good lid that snaps on nice and tight and keeps the air in. And then, of course, what you need are your antacid tablets and a little bit of water. So pour in some water and then put in your antacid tablet and snap the lid on. Flip it over and wait for the carbon dioxide gas to build up, which will build up pressure, which will launch your rocket. Ha-ha! So there you go, a chemical-powered rocket. Come on, let's max it out. So first, I need an expert to help me. Lisa from Logix Academy, of course. Logix Academy people have helped me launch all the rockets on Science Max. This is gonna be great. I'm gonna get my helmet first. Okay, let's launch some rockets! Let's go! Whoa, wow, it's really dark in this room. I can't see anything.
Bill?
Lisa?
Bill?
Lisa? What?
Bill?
Where did this come from? I guess the portal's malfunctioning. Hey, Lisa!
Hi!
From Logix Academy, great to have you here.
Great to be here.
Let's put this over there. We are here to max out the chemistry rocket!
Ooh, what is that?
It's just a small plastic container. But when we put an antacid tablet in there and some water,
We get a chemical reaction.
we get a chemical reaction, and so that's what creates the pressure, and then that pops the lid off, and we get a little rocket.
Kaboom!
But now we're going to max it out. Get a bigger container and more...
Wait.
What?
How about if we launch a whole bunch of them?
Ooh, so we just get a lot of the small one, and we launch them all at the same time.
Exactly.
Okay, great. So we just need a whole bunch of these and a whole bunch of...
And a whole bunch of science antacid.
Yeah, well, that's okay. I get them both in bulk. Come on, let's go put it together. I'm an acid, and I'm a base, and we are enemies. Whoa! Well, we're not really enemies. Yeah, that's true. It's all about how we react chemically. You see, as an acid, I really want to give protons away. Protons? Who needs your protons? Get your protons here. Protons, I got more than I want. I don't need them anymore. And bases, we need protons. We'll do anything to get them. Protons, you can protons away. I'll take some protons. You think that when you get these two together, you'd have some pretty great chemistry. But the truth is, when they're together, they often don't react. Whoa. That is until water gets involved. Once you have water, acids and bases react.
Here, take some protons. All your base are belong to us.
Here you go. Take some protons. I don't need
More. I want more. I
Here,
want
have some
more
of those.
protons.
Here.
Water is a solvent, allowing the chemical reactions to take place.
Depending on the strength of the acids and bases, that reaction can be mild. Would you like a proton?
Oh, no, really, I could.
Please take it.
Oh, well, thank you, that's very generous.
Have another.
No, perhaps, maybe I will.
Here's
Yes,
one.
Okay, maybe just one.
But if the acids and bases are strong, the chemical reaction can be really extreme.
This is what's going on in the antacid tablet, and why, without water,
Nothing happens.
Oh, water!
Water!
Come
on!
What'd you do?
What?
And that's the last one.
Lisa and I are maxing out our chemical-powered rocket not by making it bigger, but by making more of them. How many more?
400 caps all glued down, 400 antacid tablets, or part of,
Yep.
all glued down, and they're glued on this fancy-pantsy spinning surface. So we rotate this part upside down.
We fill each container with a little water and snap it on underneath. This way, the antacid tablet and the water don't mix until we flip it back over. It also allows us time to snap them all on.
Okay, ready?
Ready.
All right, 400 containers. Here we go.
Let's do it.
Once we flip the board back over, the reaction started taking place, building up carbon dioxide gas and increasing the pressure until...
What do you think?
Oh, yeah. Oh, yeah.
Oh my goodness!
It's good luck if you catch one.
Wow, that one went really high. Oh!
Awesome! That totally was great. Wow. Okay, so high fives on that.
Yep.
That worked spectacularly.
That was awesome.
So we've done this.
Let's go bigger.
Let's go bigger.
Bigger.
Okay. So let's go
Definitely.
and we'll clean this
All
up
right.
afterwards.
Yeah,
okay.
let's do it.
Okay, let it go. Whoa. Whoa. This is a balloon, and this is an orange. When you put them together, a chemical reaction happens. How'd you go in there for a minute, didn't I? No? No? All right. Well, you can actually do a chemical reaction between a balloon and an orange. You see, balloons are made of latex, which is a kind of polymer that's very, very stretchy. And orange peels contain a chemical called limonene. Limonene breaks down latex. So, we have 3 questions. The first is, why does this happen? Well, like I said, it's all chemistry. You see, balloons are made of polymers, chains of molecules held together by chemical bonds. A limonene molecule attacks those bonds. Nom nom nom, nom nom nom, nom nom nom, delicious. And breaks it, that separates the polymers, and that pops the balloon. But remember, it only works with natural latex. So make sure you're using natural latex balloons. Second question, why do they call it limonene when it's in orange peels? I mean, yes, it's in lime peels and lemon peels, but the chemical itself smells like oranges. They should call it orangenine or citrus fruitinide or... Anyway, third question, should we max it out? Of course we should, come on. 200 balloons versus 2 bottles of limonene. Ready? Go!
first attempt to max out our chemical rocket was 400 plastic containers.
Oh, yeah.
That worked well, but now it's time to make the container larger.
Whoa! Giant maxed out chemistry rocket canister. I have a big plastic container with a groovy lid that sits there on airtight, which is great.
And I have a giant jar of antacid,
How many? It was like 60 antacid tablets or something?
at least.
This works exactly the same as our smaller containers. We dump the antacid in, seal the lid airtight, then flip it over. And now would be a good time to mention not to try this at home.
Okay. Oh, it's not gonna take long. All right, so that was the canister version. Now we need the pop bottle version, the
Yes.
rocket version.
Yes.
Okay, let's go make that.
Let's do it.
Okay. This is a light stick.
It creates light using a chemical reaction. There's a liquid chemical inside and also a glass container that holds another chemical. When you bend a light stick, you break open the container and the two chemicals mix, creating light.
There you go, light sticks, chemical reaction. And yes, of course we're gonna max it out. This is a whole bunch of the two chemicals in a light stick. Let's max it out.
So how does a chemical reaction produce light? Well, a lot of chemical reactions produce energy. You might think of a chemical reaction producing heat. Well, heat is a kind of energy. This chemical reaction also produces energy, just energy in the form of light. It's just a different kind of energy.
Whoa, maxed out light stick!
And now for a Science Max quiz. Chemical change or not? What's a chemical change? Well, let's demonstrate. Look at this. It's a happy little molecule of iron. And here's another molecule of oxygen. If they were to have a chemical change, they would react and form different molecules. Look, it's a molecule of rust. Rust is a different chemical than either iron or oxygen. It's a chemical change. Now, if these molecules mixed and did not change, then it's not a chemical change, it's a physical change. Sometimes it's hard to tell if it's a chemical change just by looking, but asking what kind of change it is leads to good science. So let's look at some examples. Vinegar and baking soda. Is it a chemical change? Yes. Vinegar and baking soda react to form different chemicals. Sodium acetate, that's the white stuff that's left over, and carbon dioxide, which makes the bubbles. How about a nucleation fountain with Diet Cola and mints? Haha! A lot of people think that's a chemical change, but it's not. The mints cause carbonation, the bubbles, to escape faster. But in the end, you still have cola and mints, no new chemicals. And without the carbonation, nothing happens. So, it's a physical change. Take a guess at this one. Glow stick chemicals. Well, producing light or heat is usually a sign of a chemical change. How about mixing sugar and water to make a sugar pop? That's a physical change. You start with sugar and water, you mix them, and when you have a sugar pop, what chemicals are you left with? Well, sugar and water. So, no chemical change. It can be hard to tell sometimes, but whenever two things mix, think to yourself if it's a chemical change or a physical change. And now you know it's either one or the other. And that's the first step to good science. Thanks for playing our Science Max quiz. Our maxed out rocket worked great. Now to make it look more like a rocket.
So we have a mesh bag here to put the antacid in.
Right?
And we have some paper clips attached to it.
And what are the paper clips for?
Well, Phil, we have a magnet.
Ah!
And so the magnet sticks to the paper clip.
And so that's what we have here. You see, the bag is full of the antacid tablets, which we put through the mouth of the bottle, and the magnet is holding the paper clips on the other side of the plastic, so we can sort of move it along. So we can start with the bag over here where the water's down there, but now we attach the launcher, like so.
All this effort is to keep the reaction from happening until the bottle's on the launcher and we're ready to go.
And then, as we pull the bottle over, we bring the bag up this side, And there, the water and the antacid have never touched.
No reaction.
All you need to do now is we pull this magnet away and the bag will fall into the water. And then we will have the launcher down here. And we pull the release and the rocket will go.
We add some weight to the launcher to help keep it in place.
Okay, right, wait, glasses.
Safety first.
Okay, ready?
And then we pull the string with the magnet. That drops the bag of antacid tablets in the water and starts the chemical reaction. Because we have a latch holding the bottle down, we can wait until the chemical reaction happens fully. And there's a lot of gas pressure in the rocket before...
3,
2, 1.
1, run! Woo! That worked.
Yeah, I had hit the ceiling. I think we need to do this outside.
Yeah, I think we definitely have to do it outside.
All right, totally great. Weird. Anyway, I was saying we should put 3 or 4 of these. 3, 2, 1, go! There it is. Yeah!
We tried it outside and it worked great. The only thing left was to max it out even more.
So, larger chamber,
Yep, more antacid.
more antacid, more air, more water.
Absolutely.
Bigger rocket. Okay, so you know what? I know how to splice 2 bottles together and we can increase the size
All
of
right.
the chamber. This is sodium acetate. How do you get sodium acetate?
Well, when you do a vinegar and baking soda reaction, what you have left, once the reaction is finished, is sodium acetate. It's a crystal, and you can do something fun with it that may seem familiar. You make a supersaturated solution of sodium acetate by heating water and dissolving as much as you can, and then when it cools, you can get the crystals to reform.
Now, if you did this with sugar, you could make a sugar pop, which we've done before. If you do it with salt, you could make a salt pop, which is less appealing. And if you do it with sodium acetate, you can do this.
Just like with the sugar pop, all it needs is a seed crystal to get the crystals to reform. But unlike sugar, which takes a few days, sodium acetate recrystallizes right before your eyes. Because we heated the water, it allowed more crystals to dissolve in it.
Ooh.
But then it cooled down afterward. There's more crystals sitting around in this water than there should be at this temperature. They want to turn back into crystals, and all they need is something to start them going.
I've colored this one green because, I don't know, science. Maybe it'll look cool.
A tiny crystal on the end of the stick is all we need to start the reaction happening.
Whoa! Wow. And there you go, sodium acetate. That one wasn't done yet.
We've gone from small containers,
Oh, yeah.
to a large container, to a rocket.
Yeah!
So what's next?
Super maxed out rocket!
12 2-liter bottles all spliced together to give us a very large chamber to build up pressure with.
So the chamber is all the same. So it's all one big hollow tube, and now we're gonna fire it off. Let's go!
Let's do it.
Awesome rocket! Yeah!
Lisa and I follow the same procedure as before. We use a bag of antacid tablets held up inside the rocket with a magnet. And once it's sealed on the launcher, we pull it off, let the antacid mix with the water, let the chemical reaction happen for a while to produce enough gas pressure, and then we fire it.
Okay, here we go. 3, 2, 1, go!
Oh my God!
That is the highest I think
Wow.
we've ever shot a rocket on Science Max.
That's amazing.
Well done. Chemical reaction rocket. Thank you very much for joining us on Science Max Experiments at Large. We should build another rocket because
I
that
think so.
one is probably broken.
That's done.
Okay, let's go.
Let's do it.
All right, so this time I think what we should need to do is... Oh no, it's nothing but garbage cans in there. We gotta turn the portal off. Come on, we gotta get...
This This episode of Science Max is all about building things strong. 2,
And let's do 3.
an arched bridge, giant house of cards, magical stacking books, and more.
Oh, I thought they were gonna do it.
All on this episode of Science Max Experiments at Large.
Oh, hello, Science Maximites. We've got a lot of work today, so I was just getting prepared. You know, taking something flimsy and making it strong, that's what scientists and engineers do every day. And it's also pretty fun. You take something that's not that strong, and by the way you build it or put it together or change its shape, it suddenly becomes a lot stronger than you think it was. So I thought that's what we should do today on Science Max Experiments at Large. We should build something. So we're gonna build an arched bridge, and we're gonna build it out of sugar cubes. So here's what you need. You need some sugar cubes, you need some sandpaper, and you need some modeling clay. So first, you want to make some abutments out of your modeling clay. What is an abutment, you ask? It is this. They distribute the force laterally from one side or the other. I like to use this. This is half a roll of duct tape. And so it fits in just like that, and you see, it's a perfect arch. If you just take sugar cubes and you try to stack them into an arch, it's not going to work because the sugar cubes may not even fit all together, and you can see only the bottoms are touching. I take up the guide and it all falls apart. So here's what you do. You take your sandpaper and you change the squares into trapezoids, and you start sanding down your sugar cubes into trapezoids. Basically, you want one small side and one long side. Thin at the top, wide at the bottom, or wide at the top, thin at the bottom. It's a trapezoid no matter which way you hold it. Put it on the bridge and see. And as you go, you will see if you're doing it right, there will be no gaps. If you go to the Science Max website, there will be a guide that you can use to help you make the sugar cube bridge, so you don't have to spend as long as I did making this one. And then the most important part is the keystone. That's the one that fits in right at the top, just like that. And when it does, you can take away the guide and it stays up. Isn't that cool? It stays up without any glue, without any mortar, all based on the shape of these sugar cubes. The cool thing is, it'll hold the weight of a whole car, provided you have a very, very small car. The reason why it works is because the weight is distributed along the arch into the abutments and down into the ground. That's what makes an arched bridge so strong. And that's what we're gonna do today. We're gonna max out an arched bridge. So I think I'm gonna need some help though. Maybe Sonia from the Ontario Science Center. She really knows her stuff. Yeah, I'll go there and I'll see if she's busy. All right, come on, let's go. Hey, Sonia.
Hey, Bill, how's it going?
It's going good. I was wondering if you could give me a hand with something.
Okay, what's up?
I'm building, well, it's easier if I show you.
All right.
Do you mind coming back to Science Max headquarters? We can take the portal.
But that thing doesn't always work.
Oh, it is fine. Well, I mean, that worked just fine. Uh-oh, it usually makes a beeping when I do, oh, it's out of batteries. Oh, I told myself, Phil, charge the remote before you leave the lab, and then I...
Where have you been? Breathe.
The remote ran out of batteries, so I had to run the last 3 kilometers.
It's all right.
Because
You made it.
Long story. So the Sugar Cube Bridge, you had a chance to look at it, right? This works on any scale, right? It should, no matter what size arch, it should be the same, right?
Definitely.
Good, because what I want to do is use these abutments, but go to these abutments.
Oh.
So we're gonna start the bridge here, and I've already created a thing that we can use to put the sugar cubes on as we go up, so that we can make sure that it becomes a perfect arch. Yeah.
Do we have enough sugar for this?
Yep. I got tons of sugar.
Wow.
Yeah. So I think we're gonna need some glue because it's gonna be really hard to get these to stay.
Yep.
To stay right.
On.
there without a little bit of glue. We're gonna make a giant arch, maybe some walls, and we'll see what happens.
Let's do it.
Oops. An egg. Now you might think of eggs as kind of flimsy, and they do break pretty easily, but eggs are actually stronger than you think. It's because they're, well, egg-shaped. You see, the top of the egg is like a little bit of an arch, and the bottom of the egg is also like an arch. And arches distribute the weight, just like they do in a bridge. Here's how you can experiment with how strong eggs are. First, you want to get a pair of gloves to protect your hands from the shell, just in case anything goes wrong. You should also tell an adult that you're doing this experiment because if it does go wrong, you're gonna have some mess to explain. And also, you should probably put on some safety glasses. Now, here's what you do. Take your egg and carefully put it in your palm just like that. And put it against your other palm, and you're gonna push in directly on either side of the egg. Start pushing harder and harder. You can even lace your fingers and press even harder. And if you do it right, the egg won't break. Pretty amazing, right? So, just how much weight does an egg hold? Can one egg support my entire weight? Let's find out. I'm gonna lift my weight up like this and lower myself down. And no, cannot hold my weight. Can my weight be supported by 2 eggs? Oh, nope. Phil's weight, 4 eggs. Oh, I thought they were gonna do it. Nope. My weight on 8 eggs. Huh? My weight can be supported by just 8 eggs. Science! Whoa, careful.
Sonia and I are on a quest to make a maxed out sugar cube bridge. The reason why an arch works is because the weight, or the load, of whatever's on top of the bridge is carried outward along the curve of the arch to the abutments at each end, which carry the load and keep the ends of the bridge from spreading out. No matter what you build your bridge out of, sugar or stone, the science stays the same. Sonia and I are building a much larger bridge out of sugar cubes. We're using glue to help the sugar cubes stay together, just like stone bridges use mortar. And when we're finished, it was pretty impressive.
A massive sugar cube bridge, right? High fives for that.
The moment of truth comes when we take out the support and...
Yeah! It works! Okay. Giant sugar cube bridge. So do you think it'll hold some weight?
I think it definitely should, because right now we have an arch, perfect arch, and the weight is being distributed to the sides, the base.
So that's what it's for, right? We can put weight on there?
We can definitely put some weight.
One to start?
Let's start off with 1.
Okay.
And let's see how it goes.
All right.
Here we go. All right.
Yeah, 1 book, yeah! All right, sugar cube bridge,
1 book.
2 books.
Are you nervous?
Yeah! Sugar cube bridge, 3 books.
3 books.
Oh, that was great. It held up 3 books.
3.
Well, technically it held up 2 books and broke on the 3rd.
So it's kind of still far from how much weight we want to hold because we want to cross it.
We definitely want to cross it, so that means we need something bigger and stronger. The cube
Yeah,
works.
you're right, because the cubes are great because that keeps the science the same.
Yep.
Right? So something cubular. The milk crate, really?
Definitely, I think we should use those. It's a cube.
It is a cube. A whole bunch of milk crates, and we'll see what we can do.
I think that sounds great.
Awesome. Whoa. This is a Prince Rupert's drop.
It's a piece of glass that has a long snaky tail and a bulb at one end. So what's so interesting about a glass tadpole? Well,
I'll show you. And remember, this is just glass. Oh, Prince Rupert's drops are very strong, almost as strong as steel. It's all in how they're made. Molten glass is dropped into cold water. What happens is the outer part of the drop cools off first, leaving the inner part still hot. When the inner part eventually cools, it contracts, pulling everything in tighter and tighter, keeping it under a lot of tension. And because it's round, the force you put on it is distributed all the way around, just like the force is distributed on an arched bridge. Until you get to the tail. Just the tiniest break in the tail, and it explodes. All that energy is released in a chain reaction. Why it's so strong you can hammer on one end, but explodes when you break the other, puzzled scientists for centuries. But now we know it's all in how it's made.
The Wizard Academy. All you have to do is demonstrate true magic, and you will be granted entry.
Send in the next applicant. Okay, don't let them see you. Don't let them see you. Okay, magic smoke. And here we go. Big entrance.
Behold, it is I, Overwhelmo.
You again.
I only have to demonstrate magic one time, and you have to let me into the Wizard Academy. And last time does not count. So prepare for your mind to be boggled and your eyes to also be boggled, because I shall do a trick. I will just get to it. Here is a book, behold! And now, feast your stupefaction as I produce another book, ha-ha! And then 2 or 3 more times, behold, that's good. Behold! And now, look upon the wonderment as I stack these books on top of each other, like this. And now, feast more stupefaction as I cleverly move the books off the table. And now comes the magic word. Now, I say the magic word. The magic word! And behold, the book is levitating. It is completely off the table. I have done it. Magic!
No.
No?
Not magic, that's science.
But the book is levitating.
No.
Look, it's not even touching the table.
No, it's being supported by the books below because of the center of mass.
Preposterous.
I'm afraid it's very posterous. Each book is balanced on the one below in a way that the center of mass is behind the edge of the book below. And the entire stack's center of mass is behind the edge of the table. So it may look like magic, but it's science.
So, I can't get into the Wizard Academy?
No, I'm afraid not.
Good. Alakazam! You will rue the day that Overwhelmo did not. I will return, and then you will see. Oh, ow.
Sonia and I made a large bridge out of sugar cubes, and it didn't hold much weight. So now we're going to try making another arch bridge, but instead of sugar cubes, we're going to use milk crates.
There we go. I've made some abutments out of giant crates, and this is where we're gonna start our bridge, and they start there, and it goes in a big arch, but we're gonna be using
I brought milk crates.
milk crates. High fives, high fives.
So we start our bridge,
This is a straight line, it's not an arch.
It's not an arch.
but it's clear we have a problem.
Okay, ready?
That didn't work, Phil.
It's like we're back to the beginning again. This is like 2 straight
We
lines.
got 2 straight lines,
It's
yep.
like a triangle.
We need an arch, so we're gonna need a support.
Sonia and I build a support to help us make a curve the milk crates can follow. But after we finish stacking, there's a problem.
It doesn't look very solid.
Yeah, it doesn't, does it?
Here.
Oh, yeah. Because there's a gap at the top of all of them. Look, that one, there's a gap. There's a gap there.
There's a big
a
one
gap there.
here. It's
Well, I
not
mean,
making our bridge very solid.
There's only one way to find out for sure,
You can try it.
is to pull this out and see if it stands up.
Let's do it.
Okay. So, didn't stay up.
Didn't stay up.
Okay.
That's all right, though.
I'm not sure
why it isn't staying up. Like, the sugar cubes were cubes.
That's a cube,
Milk crates are cubes.
but we did change the shape of the cube.
Oh, yeah! If you remember, when I first built my sugar cube bridge, it didn't work with cubes. You have to sand the cubes down to make them into trapezoids. You can't build a perfect arch out of cubes.
So they were tall, wider here and then narrower there so that they had... Oh, so that's the problem.
Yep.
So I could, like, cut it? I could cut it. I could cut it.
You could.
I could cut it.
That's gonna take a long time, though.
If we cut the milk crates into trapezoids, everything will work, right? Right? We take a milk crate and with the right safety gear, we cut it so we can reshape it into a trapezoid.
Good.
And it works. But
It's gonna take a long time, isn't it?
Definitely. So how about this? I have an idea. So remember when we did the experiment and we had lots of V gaps?
Yeah?
How about we put some wooden wedges into those gaps to make it one secure structure?
So it was sitting like this.
Exactly. So what we're gonna do is insert wooden pieces right here, so we'll fill those gaps.
I get
and
it.
we'll make it one secure structure.
Ah, instead of cutting all of our milk crates, we can keep the milk crates.
Yep.
And they can be solid and we just add to it rather than take away.
Taken away, exactly.
That is a smart idea. Okay, let's make some wedges.
All right.
Oh, hey, how you doing? Let me guess, you want to build a strong structure, something that'll stand the test of time. Well, you know you gotta use the right kind of shapes. Look at this, a square. Now, squares have gotta be strong, right? Well, maybe. Maybe if you press straight down on it, but watch as I push to the side. Oh no! The thing that I have built is now collapsing because squares aren't in fact strong after all. If only I had listened to Sal's sage advice. Yeah, squares aren't gonna cut it. Fortunately, there's a shape that's strong in all kinds of ways. A triangle. Okay, so you heard of triangles before, good for you. But look at this. You can push down from the top and it doesn't move, or you can push from the side and it doesn't move. Triangles are awfully pointy. How do I build with them? Observe! Ha-ha! Triangle here, triangle there, platform on top. And watch. No matter how I try to shift it, it stays solid. And check this out. Triangle here, second triangle there, and a third triangle shape here. That's like 3 triangles for the price of 2, huh? That's a good deal. So there you have it. The triangle, one of the greatest shapes to build with.
This is a house of cards, and if you've never built a house of cards, you should definitely try. Try, because it's not easy. What you need to do is you need to make triangles with the cards. If you do it just right, they'll stay up. Then you take another pair of cards, like that. You take another card, and you put it on top. And it stays up.
keep on building by making triangles and putting another card across the top like a roof.
Then, when you're ready, you can start to make a second layer.
It takes a lot of patience to make a house of cards. But with enough patience and really steady hands, you might be able to finish it.
There we go. Ha-ha, a house of cards. Now, let's max it out. Shh, backing away slowly. Backing away slowly.
To build our maxed out card house, the Science Max build team and I used large pieces of foam insulation, which were super light and easy to work with. Once we set up the first layer, we needed to bring in a scissor lift so we could keep building the next layers. By the time we got to the top, our card house was 10 meters tall.
Yeah! Giant house of cards! And now that I've built a giant house of cards, what do I do with it? I knock it down. Science! I'm gonna build it again.
Sonia and I are rebuilding our milk crate bridge. Since cubes don't work if you're trying to make an arch, and changing the shape of each milk crate would take too long, we're using wooden wedges to fill the gaps at the top of the milk crates.
Once we get the wedges in, the milk crates have support at their tops and they make a perfect arch.
Are you ready?
I'm ready.
All we have to do is pull the wooden thing out, and if it holds up on its own, we've done it.
We pull out the support and
It stands!
it works! The bridge supports itself! Now it's time for the final test.
We try to walk on this bridge.
So we spent some time making sure our bridge was safe. We added a crash mat and
We built a second arch
We sure did.
so that it's a little bit wider, and it feels very solid. So the only thing to do now is to test it.
Test it out.
You gonna do it?
I absolutely will.
All right.
Sonia puts on a helmet and gives it a try. And sure enough, it works!
Yeah! Milk crate bridge! 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 Woo-hoo-hoo-hoo! Science Max experiments at large. Milk crate bridge!
Yay for science!
High five! High five!
High five.